Hello. Welcome to the extension video of the traffic light question. Has the question got you stumped? If you have answers, just keep them in mind as I run you through the solutions and see whether your guess is correct or whether you're at least thinking along the right path or not. All right. So if you're not sure about what question I'm talking about, this is a traffic light question where we will use a comparator operational amplifier to change when how long the red LED turn on and how long the green LED turn on. So the original question kind of looks like this. All right. So if you can see in this graph, okay, let me make my head smaller, blocking the view. Okay, there we go. You see in this big, beautiful graph, right, there is a 1.5 volt, which is your V2 or your V plus. So in case you've forgotten your comparator circuit, it looks something like this. Okay. So there's V plus and there's V minus. So this V plus is V2, this one is V1. So obviously the sinusoidal curve is V1, all right? And the output is drawn in the question. So go watch that video first, then come back again, all right? Then I'll run you through the actual question. So this is minus, this is plus, and the supply is plus minus 5 volt. All right, so this is the actual circuit drawing. All right, and I have asked you, what do you think will happen to the duration of the red LED emitting light when V2 is increased, V2 is decreased, meaning this blue line, I drag it up or I push it down. Now, my friends, in this case, right, it's probably quite important as well for us to think about it along the lines of like, actually, what is happening here? Right, we are comparing this sinusoidal wave, which is V1, and the straight line wave, which is V2. Okay, so when comparing them, whenever the blue line is above the red line, the V out is positive. So say from here to here, roughly speaking, here to here, your V out is positive 5. Okay, and whenever the blue line is below the red line, say from here to here, your V out is negative 5 because your op-amp will saturate. Think of all the previous example. Op-amp will saturate whenever the V out is, whenever the V plus is bigger than V minus or V minus is bigger than V plus. All right. So if I continue this trend, I will get a graph that looks like this. So this is how the graph look like. We have drawn this in the previous videos. So you can see that there's a certain longer time interval where the red will turn on. I highlighted red here because the output is positive 5 volt. Right? And the time interval for green, this part here, this part is shorter. So the first question I ask is, what happens to the interval of this red one if your V plus is increased? Meaning I bring this one and I push it upwards. If I push this blue line upwards, this is essentially what I will. Okay, now you can see there's a second graph beneath here. The blue line is pushed upwards. We compare the top graph and the bottom graph and see, right? So here, this blue line bringing upwards, meaning your V plus has increased. Okay, so if you're wondering what value this V plus is, I hop on Desmos to draw this. I mean, I didn't code it. I manually highlight by hop on Desmos to draw this. This V plus is now 2.4 volt. So if now this is 2.4 volt, your V plus increase, you notice that the time for the RLED to turn on is longer. Because now the duration of V plus being bigger than the sinusoidal wavefront will be longer. Okay, the sinusoidal wavefront, if you're wondering, right, the amplitude for this baby here, if you go and check out the graph, okay, I'm not going to scroll too much because, you know, lag. This amplitude is actually 2.8. Okay, so it's just slightly below, all right? So this is part A. If your V2 increase, this means your non-inverting input increase. This means that there is more time where V plus is greater than V minus. There we go. Took them that long to change color. Okay, so there will be a longer time where your V plus, which is your non-inverting input, is greater than your V minus, which is your inverting input. So this means what happens to your output? Okay, so this means that your V out is equal to positive 5 volt for a longer time, meaning the R LED is turned on for a longer interval, longer time interval. Okay, so this is basically the idea. If you move the blue one up, of course, there will be longer time intervals where the blue line is above the red line. So you can compare this graph, all right, and this one, the top and the bottom. Okay, then second part, right, I ask you, what happens if V2 decrease? Then the opposite will happen, no? Right? When I pull the blue color one down, this is what I'll get. Okay, so you can see from the third graph, right, I have moved this blue color line downwards. So I have decreased my V plus. My V plus now, if you are wondering, is 0.5 volt. So the times where the sinusoidal wave is above 0.5 volt is longer time. Okay, the horizontal axis is time. So from here, so in case you don't know, this is P and this is V out specifically, or all the potentials lah. Okay, so your V plus is 0.5. So you can see that the red time interval is shortened. So it is the same explanation. So normally in the exam, they won't ask both lah. They will just ask you to state and explain. So here are two ways they can ask. Number one, they could ask like the way I've asked. State and explain the effect of decreasing the non-inverting input from 1.5 volt to 0.5 volt on the red LED, or decrease. So if V plus decrease means the time for positive to be, for the output to be positive will be less. That is one way they can ask. The next way that they can ask is state the changes that can be made so that the red LED turn on for a longer or a shorter period of time. So this is the easiest one to change lah. Okay, longer and shorter period of time without altering the alternating current. Because this sinusoidal shape, right, if you want to change, or sometimes you need to think a bit longer. That one we'll go into it later. Okay, so from here we're going to write the explanation for this first. This is for part B, I think. So you can say that when V plus decrease, okay, or V2 decreases, then your V plus is less than V minus, or rather, I would just say that what did I say on top? I want to copy the sentence. More time. So this one is less time. Less time or a shorter time interval where, zoom in a bit, where your inverting input, your non-inverting input is greater than your inverting input. So I can say that V out is positive 5 volt for a shorter time interval. If V out is positive 5 volt for shorter time interval, then what can you conclude? We can obviously say that the red LED is on for shorter time interval. All right. So if I zoom out in this part, then you can actually tell the difference. Okay, so let me zoom out. Don't compare the one on the left first, just compare the first three on this side, on the left side, sorry. So if you look at this one, this is the original one. If I increase the blue line, the position of the blue line, this red line become thicker. When the band become thicker, red will turn on longer. I decrease the blue line, the band become thinner. Red will become shorter. All right. And then this is bonus for you. Because remember, I sneakily say, I don't have to think so much. You go and take out the battery, the power supply, or the potential divider. Because this 1.5 volt or could be supplied by a potential divider. Okay. So later we'll discuss some example where we use a potential divider to choose a set voltage. Because in this circuit, they didn't actually tell you how they put this 1.5 volt. They could connect this to a battery. Okay. They could connect it to a potential meter. Potential meter is always more stable than the battery. All right, anyway, let's say I flip it. I flip the battery, let's say it's a battery, and I flip it so that now the voltage V plus is not positive 1.5, but negative 1.5. GG. Okay, so you can see here, this means when it's supposed to be red, it becomes green. When it's supposed to be green, it becomes red, and you kind of like get a graph that looks a bit like this. Okay, which is pretty cool, actually. So if I flip this to negative 1.5, since I started drawing from here, okay, so you can see that the green part will turn on generally when the red part is supposed to turn on. So you can compare this one here. This part is supposed to turn on red, but this part is now green. Okay, so when the green and red turn on, will be inverted. Very nice. Okay, so for this one, this is part C. You can say that the part C, whoops, what happened there? Okay, my computer, as you can see, obviously freaked out a bit. It's going to keep freaking out until I replace it. So please bear with us, because I can't possibly fix this problem. All right, so this one, this particular graph, is a special case lah. I don't know what else to call this. The A, B, C, D. Okay, in this case, what happens is I reverse the polarity of the input voltage to V plus. So right now, your V plus, instead of positive 1.5, it is negative 1.5 volt. So this one is negative 1.5 volt now. You go and hack the traffic light. See now, green for such a long time. Easiest thing to change, okay? So if you, let's say your input, this V plus, is actually attached to a potential divider, you can actually connect it to a variable resistor. Think about it. Possibilities are endless. Let's say you have a potential divider like this. Okay, potential divider. I mean, I guess I could draw it the normal way you tend to see it. Okay, hang on. Let's say you have a potential divider, right? You know a potential divider like this. Then I don't know what you want to put here. A variable resistor also can. You want to put thermistor also can. So you want the traffic light to turn color faster when, I don't know, when it's hot outside, when it's cold outside. Or you could have a LDR, you know, LDR. So all these you connect to V plus. These are all your V plus connection. Aye? And then here you connect to another resistor lah. Doesn't matter. And then you ground it. So you can connect this to another resistor. Then you ground. So based on this potential divider, right, you can use different kind of sensing device. You can even put a strain gauge there or piezoelectric transducer. How do you think all the what's that thing? The pedestrian crossing one work? Maybe someone press it and then it will trigger some motion detection. Don't know. Right, every circuit is different. But here you can see this V plus, right? The possibilities are endless. You can change it any way you want. All right. So what I'm saying now is that let's say I reverse the polarity of this V plus. Okay, maybe here I swap lah. Whatever power supply I put here, let's say this is positive V. I just change out this power supply and put negative V. Oh, sorry, negative 5. Why did I put negative 5? Negative V. Okay, it doesn't matter. So just follow the question. If they change it to negative 1.5, you just take their word at as is. But don't forget, these are all potential dividers and we can change it however we want. All right, don't worry. You got this. It's just ratio. So for this case, you will notice that when, as mentioned just now, when it's supposed to be red, it becomes green. Now, when it's supposed to be red, it becomes green. Okay. Actually, you should check down here lah. See here. When it's supposed to be green, it becomes red. So the interval for R will be shorter and the interval for green will be longer. Okay. It's not exactly timed perfectly because the interval, the intersection time is actually different. But what I could say here is if we reverse this, then the R will be on at the shorter time interval. G will be on at longer time. Okay? And the last and final one that I asked you is what happens if I increase the frequency of this sinusoidal alternating current. Well, I have taken the liberty to graph it for you, so you can check it out here. All right, so if we increase the frequency, I just increase it slightly lah, so that it doesn't look very intimidating. And I also don't have to highlight this until I cry. So when we increase the frequency, what you will see is that the switching over time will be very fast. So green still will be turned on longer than red, but the changeover time is very fast because now you oscillate more times. All right. So I would say that the duration of R will still be shorter, but the changeover is also faster. Okay, meaning you can see this one, it took like 4 boxes for it to change over, and then this one only took 3. Okay, this one took 4, almost 4, and this one took 3. So I think I'll write that down. This is part C in my extension question. Replace, okay, this one is V plus, this is V minus. Replace V minus with higher frequency AC. So what will happen here is you will say that the R LED will be on at a shorter time interval. Okay, and the second reason why this R LED turn on the shorter time interval is because when the frequency of the V minus increases, okay, frequency of V minus increase, what will happen is that the switch over happens more frequently. In the same time interval. So all this graph, right, I crop roughly 25 seconds. Okay, so you can see that this one 25 seconds, I switch over 1, 2, 3, 4, 5 times, whereas this one I only switch over 4 times. Okay, so if you increase the frequency of the AC, the red light, green light will change color 5 times instead of 4. Whereas if you look at this, you compare this one left and right, once it loads, you will see that they both change the same amount of time. It's just that instead of red become green, it becomes green become red. So from here, red become green, but here it's green become red. Then red become green. So 1, 2, 3, 4. 4 change over. 1, 2, 3, 4. 4 change over. This little sliver here doesn't count now, okay? All right. So these are all the extension possibilities. And of course, you can probably tell the possibilities are endless. All right. So just to recap, for the first 3 ones on the screen, the one on your left, this one is the original one. Okay. And when I increase my V plus, which is basically increasing the value of the constant line, then the red color will be longer. The green color will be shorter because the times where the output is positive is longer. If I decrease this blue color line, then the red color will be shorter and the green color will be longer. When we say longer and shorter, we are comparing to the original one, which is the first one. This is the original one. Let me write that down. If it allows me to write. This is the original. Okay? And if we swap from positive to negative, then what we are essentially doing is we are allowing the green light to generally turn on when it's pink and red to turn on when it's green. But it's not as straightforward as it will have the same. Does it have the same? No, it does not have the same switch over time because of the periodicity of this sine curve. So if you're even one step more advanced than your friend and you want it to change over at the right time, sine curve is not the right curve to use. Cosine is the right one. Okay, but that one is a bit too much, so I shall not delve into it. The whole idea here is right now the number of switch over is the same. It's just that now green will dominate lah. Okay, because now I've decreased it even further to negative 1.5. And the final part is when we change the frequency, okay, the time interval will be shorter, okay, not because we change this V plus or we change any values. When we increase the frequency, we switch over more times. When we switch over more times, the time when the red LED turn on here will be shorter than this one because the switching over happens quicker. All right, so these are all different questions that they have yet to ask for the comparator circuit. And the thing about op-amp is that sometimes they just like to ask a little bit more for you to explain, another 2-3 marks like a dessert at the end of your paper 4 question. So keep that in mind. You got this one. You have enough information to answer it. Just that maybe you never thought of it that way before. So that's why I record all these extension questions to help open your brain and also to teach you how to hack traffic lights so that you get this one and not this one. All right, so that's all for this extension video. Go and watch out and check out the other comparator circuit. If you find this useful, I wish you all the best in your A2 studies. Do share our videos with your friends so that we can learn A2 physics together. Let me know, talk to us. I'll see you in the next one. Take care now. Bye bye.